Do you already have the rights to share your screen?
Okay.
Great. Wonderful. Okay, so it's 9 o'clock. I suggest to start. Welcome everybody to this morning's lecture session in our conference on one-parameter semigroups of operators. So this is Adam Bobrowski talking now, and he's going to speak about semigroup-theoretic approach to thin layers. Adam, please, the stage is yours.
Well, thank you, Johan, and first of all, thank you, organizers, for inviting me to speak. I hope I'm being heard clearly.
I can hear you.
Yes. Okay. Mm-hmm.
So this is my talk is based on my recent research on so-called thin layer approximation, and I will give you a bit of a biological background for that and just a glimpse of history. But let me start with so my outline is I would tell you a bit about semigroup theoretic methods, and then tell you about the background in biology, and then we'll tell you about a somewhat surprising and I think even beautiful result about the behavior of boundary and transmission conditions in the thin layer approximation. The bottom line is that what is described by boundary or transmission conditions in the approximating equations jumps into the master equation in the limit. That's the main topic, the main theme of my talk. Okay, so let me start with the throtter, kato, Neve, Sova, Kurz theorem, very well-known theorem from the semigroup theory. It says that if we have a Banach space and equibounded semigroups in this Banach space, I will always denote semigroups in the form of the exponent. So e to the power ta means that this is a semigroup generated by A. So we have a family of equibounded semigroups, and we have something that we think of as a limit semigroup, and then convergence of the semigroups is equivalent, 1.1, is equivalent to convergence of resolvents, 0.2, and some kind of graph type convergence of generators. The point equivalence of 1 and 2 is due to Trotter, Kato, and Neve, and several years later, the graph convergence equivalence was provided by Sova and Kurz independently. And everybody who is familiar with this theory knows that as a bonus, as a kind of bonus, we obtain that the limit in point 1 is uniform in bounded subsets of real half-axis. So in other words, uniform in almost uniform in time. It is usually phrased. It seems to be a bonus, and it is a bonus in a sense, but it also is the biggest weakness of this theorem. Namely, if you look closer at this theorem, this cannot be improved. In other words, and there are several things hidden here. In a way, you assume you know the limit semigroup, and this is why convergence of resolvents is equivalent to a convergence of semigroups, because the limit pseudo-resolvent has very, very, very good properties. So in other words, what I'm trying to say is that in many cases, the limit semigroup, even if it exists on a smaller subspace of the original Banach space. So the picture shows that we have a subset of the original Banach space where the semigroup is where the limit semigroup is defined. And quite often, we have convergence of semigroups of the form given in equation 1, where P is a kind of projection on a subspace of the Banach space. So the limit semigroup e to the power Ta is defined only on a subspace, and then, of course, you cannot have convergence for T equals 0 if 1 is to hold true. And of course, you cannot have uniformity with respect to T around T equals 0. And there are, of course, some theorems which allow dealing with such situations. And notably, there is one theorem of Thomas Kurz from 1970s, and it says that condition 1 is implied by the following 3. And it should be noted here that while Trotter, Kato, Neve, Sova-Kurz theorem gives necessary and sufficient conditions, there are no necessary and sufficient conditions for this situation. We have some necessary conditions like convergence of resolvents, but there are no necessary and sufficient conditions at the same time. So Thomas Kurz's theorem is a sufficient condition, but very useful one. It simply says that besides convergence of resolvents, you need to have convergence of resolvents of should I say, rescaled family of semigroups. This epsilon that you see in the second condition before A sub epsilon is a kind of rescaling or transform of time, or kind of slowing down of processes related to the semigroups. So such rescaled semigroups need to converge also, and need to converge to something quite particular, namely to the resolvent of a semigroup that is asymptotically stable, in a sense that the limit that you see in point 3 exists. And this limit gives a projection which appears in point 1. So both P's are the same. Okay, so this is quite well-known theory. And if you want to look into books, there is a number of them. There is, first of all, there is Etier and Kurz's book, very famous, and it gives tremendous applications of this theory to Markov processes. There is also a book of mine, published 5 years ago, and this focuses on applications in biology and other fields, mostly in biology, but not limited to biology. There are also books like Olaf Post's, and these are related to subjects that I will cover in a later part of my talk. And there is, I also show the book of Jacek Banasiak and Mirek Lachowicz, although probably, I'm not sure right now, but my guess would be that even the word semigroups does not appear in the book, but as you have probably noticed from my talk, this irregular or irregular convergence of semigroups is very much related to quote singular perturbations and methods of small parameter or Chapman-Enskog expansion asymptotic analysis. So this is such subjects are covered in Jacek Banasiak's book. So anyway, perhaps I should come back here to this picture. If you want to keep a good example in mind, you may think of a situation where, say, initially you deal with a Banach space of, say, functions of two variables, and in the limit you have functions of one variable. Or you may think that you have two initial conditions, like in hyperbolic problems, and in the limit you have one initial condition, like in a parabolic problem. So this kind of degeneration of a state space, or so-called state space collapse, is something you could keep in mind while listening to this talk. Okay, so coming to my second topic, thin layers in biology. The entire subject started with a 1992 paper by Hale and Rogel, if I pronounce these names well, properly. And this is a very famous paper about partial differential equations in thin domains. And of course, when I started doing research in this field, I had no idea that there was such a paper like that one. And this was, in a sense, profitable for me, because I was completely unaware of a growing and huge literature on the subject. And luckily, I just didn't know that there are things that should be done. I just, in other words, what I'm trying to say is that in this growing literature on thin layers, motivations came mostly from physics and other applied sciences, but rarely or almost no from biology. And surprisingly, all boundary conditions that were being considered were boundary conditions of Neumann type. And so the phenomenon that I'm going to speak about was simply not discovered, was simply not mentioned, not even thought of. Okay, so here is my starting point. This was a paper by Tomasz Lipniacki and his group. Tomasz Lipniacki is a physicist who works in biology, and he is also very well educated in mathematics. So he uses mathematical tools to describe biological phenomena. Okay, and the subject of his paper was kinases. You may think of them as small particles living in cells, and the role of kinases, at least in this model, is to transmit signals. Okay, so you see a cell that has some receptors on its membrane, and there is some signal transmitted to the cell by activating the receptors. Now, a kinase that is diffusing in the cytoplasm, after touching an active receptor, becomes activated, and then after touching a phosphatase that diffuses also in the cytoplasm, is deactivated. So we have a very simple model here, in a sense. We have just a reaction diffusion equation as visible on the screen. But everything that is interesting happens on the boundary. Namely, we have the following boundary conditions. One boundary condition is on the nucleus. Nucleus is a kinase cannot permeate through the to the nucleus. So it's at the boundary at the nucleus we have Neumann boundary condition, and on the outer brim or outer boundary is this is a kind of Robin type boundary condition. A and R are constants, and since we think about active kinases, and they are assumed to be normalized, or the number of active kinases, number of all kinases is assumed to be normalized to 1. The first boundary condition, which is on the outside brim, tells us that a kinase may be activated by touching a receptor, or but the more active kinases we have close to the border, the smaller is the fraction of them that can be activated. Okay. So this still is quite simple, and I have not touched the main point yet. Namely, this is not just a cell here. We have a B lymphocyte here. And B lymphocytes are cells that have extremely large nuclei. So a nucleus is like, I believe it's over 90% of the radius. So the radius of a nucleus is like 0.9 of the radius of a cell. And if you remember that even kinases have some dimensions, you kind of tend to think that that they diffuse in a very thin layer between the nucleus and the cell and the cell border. So in other words, what we are facing is a situation where if you imagine a cell as a ball, then you have diffusion in a very thin layer between two balls, one of radius small r and the other one of radius 1. And you tend to think about what happens when r goes to 1. In other words, the shell is very, very thin. And why should we think about this limit? It is because this geometry influences the way kinases transmit the signal. So, and Tomek Lipniacki has thought about it, and he has made some simulations, and there were several attempts to find the limit equation, and all of them failed in a sense that simulations did not prove that this limit equation approximates diffusion well. But the final result was what you see on the screen. LB stands for Laplace-Beltrami. So in other words, okay, maybe I should go here. So the first term here is not surprising. Since we have diffusion in 3D region, in the limit we should have diffusion on a sphere. So Laplace-Beltrami is not surprising here. The third term is also quite natural. This is simply the same forcing factor, or the term describing dephosphorylation or deactivation of kinases. What is most interesting in this situation is the second term. And if you look back at the original model, you see that AR times 1 minus K is precisely the right-hand side of the boundary condition that appears in the approximating equations. Okay, so in other words, what we have here is that the second term in the limit master equation is a direct consequence of boundary conditions. In other words, what was described by boundary conditions, the process of activation of kinases, becomes now a proper part of the master equation. Let me also say a little bit about the proof. Of course, just the idea of the proof. First of all, if you want to have such an approximation, you cannot just simply go with R to 1 without changing anything. The reason for that is that if you squeeze the shell, if you make it thinner and thinner, diffusion will become faster and faster. In a sense, that it will touch the boundaries more and more often. So the stream through the boundary will become infinite in the limit. So this necessitates scaling of the outer boundary condition. Namely, you need to multiply the right-hand side by 1 minus R so that the stream through the boundary will remain roughly the same. And so this is a technical, but important information, that you need to scale the boundary condition somehow. And the main idea is as follows. The main idea of the proof is as follows. If you, instead of thinking that the shell is thinner and thinner, we look at it, so to say, through a magnifying glass, and then we see that the thickness of the shell is constant in time, doesn't change. So we use a magnifying glass that is stronger and stronger, so that the thickness stays the same for us. So we have a kind of reference space where the thickness is the same. But this, if you look through a magnifying glass like that, all you see is that diffusion is faster and faster in the radial direction. In other directions, it stays the same, but in the radial direction, it becomes faster and faster. And if you remember that diffusion kind of averages out as time goes on, or if it is faster and faster, as I said, then it becomes almost obvious that functions that are defined in such thin shells become independent of the argument that is the radius. So, in other words, these functions lose dependence on one variable. Instead of functions of 3 variables, which are functions defined on a shell, in the limit we obtain functions on the sphere, which are functions of 2 variables. So that's the main idea. Again, having thinner and thinner shells is equivalent to faster and faster diffusion, and fast diffusion averages things out, so we lose dependence on one variable and obtain functions of two variables instead of functions of two variables. Okay, and why should we think about situations like that? Well, the point is that in biology, many regions have one dimension larger than the other. And so it just, there is a number of situations where you can think of thin layer approximation. There are membranes. So this is an entire world of possibilities. And let me just point out some of them. You may think of two parallel planes and diffusion and reaction diffusion equation in the region between these two planes. And as epsilon, and suppose we have some kind of Robin type boundary conditions on the upper and lower planes. And again, if we scale these boundary conditions by multiplying right-hand sides by epsilon, where epsilon is the thickness of the domain, then in the limit, we'll obtain a reaction diffusion equation on a plane with two additional terms. In the in the approximating model, we have just f of k, whereas in the limit, we'll have also g and h. And these g and h come from boundary conditions. Okay, so this is about boundary conditions. As you see, boundary conditions jump in the thin layer approximation. Boundary conditions jump into the master equation. So that's the take-home message. But in a sense, I didn't like this result because this result is kind of asymmetric, so to say. And I started to think about the situation of semi-permeable membranes, which is in a sense also more natural. Please note the change of notation. I no longer think about kinases. I just have U. So instead of K, I will just have U. And again, I have a reaction diffusion equation in a thin region. And this, you may think of a cylinder cut through by a plane. And this plane depicts is a model of a semi-permeable membrane. This means that particles diffusing in the upper region heat the membrane many times. And this number of times they heat the membrane is accounted for by so-called Levy local time. And when a sufficient time elapses, a particle filters through the membrane to the lower plane. So these are transmission conditions on the bottom of your screen. They say precisely what I have just said, that a particle diffusing in the upper part may filter through the membrane to the lower part after some exponential time with respect to the local time. and also when in the lower region, it may filter through to the upper region with different with different coefficient describing permeability. So alpha and beta in the lower part of the screen are transmission coefficients, and the larger they are, the larger is permeability, and the smaller they are, the smaller is the permeability, and they are also if alpha and beta are constants, you may think of them as parameters in exponential variables describing the time when a particle filters through the membrane. And I didn't say that, but the upper and lower parts of the cylinder, or bottom and top of the cylinders, these are governed by Robin-type boundary conditions, which if C plus and C minus are positive, this describes loss of particles on these lower and upper parts, or if they are negative, then this is an income of particles. But since we have already dealt with boundary conditions before on the previous screen, I'm not going to pay too much attention to this because this phenomenon is quite well known already, at least from the previous slides. Okay, so what will happen if, again, the question is what will happen if epsilon goes to 0? Epsilon is the thickness of the cylinder, or the height of the cylinder, if you will. Again, we need to scale boundary and transmission conditions by multiplying, supplying epsilons to the right-hand sides, as you see on this screen. And if you let epsilon goes to 0, let epsilon go to 0, in the limit, we'll obtain a new master equation, and this master equation will describe diffusion on two sides of the membrane. If you look at the previous picture, you see that functions defined on the cylinder will be functions of three variables, say x, y, and z. Now in the limit, we will have functions of two variables, just say x and y. The z variable, being the height, has disappeared, but we still need to distinguish between the functions that are defined on the upper part from the functions that are defined on the lower part of the membrane. And this is quite interesting. The permeability coefficients, alpha and beta, or functions, if you will, they form a matrix here. And this is well known from the theory of stochastic processes, that such a matrix is related to a two-state Markov chain. So if you forget about dependence on x and y, and alpha and beta are constants, then this master equation tells us that a particle diffusing on the, say, upper part of the membrane after exponential time with parameter alpha jumps to the lower part of the membrane and diffuses there. And again, after exponential time with parameter beta spent on the lower part of the membrane, a particle jumps to the upper part and starts to diffuse there. The alerted C plus, U plus, C minus, U minus in the equation, they again describe the fact that there could be some loss of probability mass on the upper or lower parts, and they just jump to the master equation as before. So now you probably see what I meant when I said that that the previous case was less symmetrical. There is more symmetry here than in the previous case. We do not have just loss or gain parts in the master equation. We have simply a Markov chain or a kind of balance here. What is interesting, if you know just a little bit about transmission conditions and the way processes behave on the boundary, you realize that transmission coefficients, which give description of a process in terms of a so-called Levy local time, in the limit become jump intensities, and jump intensities is something that we understand in terms of normal time. So in other words, the main point here is, so the main mechanism here is that boundary conditions describe reality in terms of local time, but jump intensities of a process, they describe reality in terms of normal time. And they are just two sides of the same coin, and you will see more about it in a moment. But before I will say that, I will expand on that. I would like to mention that the theorem that you have just seen is robust to a change of transmission conditions. And what I mean by that is that you may, instead of boundary conditions that you have seen before, where are they? Right here. They are. You may think that they are. We may think that these are kind of Robin type boundary conditions. They can be changed. They may be modified to look like this. I know that they look scary, and they are scary. These are more of Feller type, and are related to stickiness of a membrane. In other words, there could be a portion of a membrane that has a kind of glue on it, and a particle diffusing in the thin layer may, after touching the membrane, may stick to it for a moment and be released after some time. And again, the limit theorem is precisely the same. Well, in a sense that the master equation is not changed. In other words, the limit semigroup is the same. All that is changed is the projection. If you remember the setup that I have presented at the beginning, the main roles played here are by the first of all, a subset of the original Banach space, secondly, the semigroup, and thirdly, the projection, which is called P. My main point in saying that my theorem is robust to a change of transmission conditions is that in this approximation, A does not change, the subset doesn't change, but all that changes is P, the projection. And you probably you can probably guess that I'm sorry, I need to go back. Can probably guess that this P is kind of averaging. in a sense, it's just integrating a function over an interval. Now, boundary conditions change this in a sense that it's not just a Riemann integral over 0, 1, say, but a kind of combination of a Dirac measure at 0 plus the Riemann integral. And of course, P and Q play a role here. So again, this is quite interesting that the limit equation is precisely the same, but all the changes is P, or in other words, all the changes is the initial condition, because that's P gives an initial condition for the limit process. Okay, and I hasten to add that there is nothing three-dimensional in this theorem. You may do similar things in 2 dimensions. So here is a case study of a similar situation. Just imagine a region between 2 circles that are here drawn with solid line, and they are of radiuses small r and capital R, and between them is the membrane denoted by a dotted circle, and this is a membrane of radius 1. And again, we have diffusion in 2 regions between these circles. And we have a possibility of filtering through the membrane from the upper part to the lower part and vice versa. And on the outer borders, we have Neumann boundary conditions. So this is a very similar situation to the previous one. But here we'll play a little bit with different possibilities. First of all, so here are 3 scenarios. In the first scenario, we will have both layers will be thin. In other words, both small r and capital R will go to 1. In the second scenario, we'll have only one thin layer, namely the upper layer will be thin. The lower layer will stay the same. And finally, in the third scenario, the upper layer will be thin. The upper layer will be thin. The lower layer will be of constant size, but diffusion will be faster, and we'll have completely different state spaces in the limit. The first one, in the first case, we'll have 2 circles. In the limit, in the second case, we'll have a circle accompanied by a region between 2 circles. And in the third case, we'll have a circle plus a point. And of course, the master equations in these 3 scenarios are going to be different also. So here is the first limit. We have thin layers between 2 circles again, and both thicknesses go to 0. But we'll also add a parameter that says how thicker the outer thin layer is from the lower thin layer. So this is gamma. And as you probably expect, in the limit we'll have Brownian motions on 2 circles separated by an invisible membrane. And what happens is that while diffusing on the upper layer, upper circle, the process may jump to the lower circle, and the intensity of this jump is alpha divided by gamma. So, in other words, as in the case that I have covered before, if both layers are infinitely thin, but in a sense, one of them is thicker than the other, then you need to, this intensity of jumps will be smaller than expected, because in a sense, particles touch the boundary less often than they should. So this is the only change here, but again, we again have a limit theorem which says that diffusion in 2 dimensions may be approximated by a diffusion in one dimension. Yes, and again, transmission conditions jump into the limit equation as proper factors of the master equation. Here is the second situation. Here, the upper annulus is thinner and thinner, and in the limit becomes just a circle, but the lower one stays of the same size. So in the limit, we have a system of partial differential equations. One of them describes diffusion on a one-dimensional, say, manifold, and the other one is just a 2D partial differential equation. So we have a system of coupled partial differential equations, and each of them has quote different dimension. And it is interesting to note the way they are coupled. The first, if you look at the first equation, it says there are the second term here is just the value of the function on the lower region evaluated at 1. So in a sense, on a border between 2 regions. So in the first equation, we have a direct coupling with the second equation. But if you do not look at the boundary condition, it seems like the other equation is uncoupled from the first one. Well, it is coupled by a boundary condition. And it is interestingly, both terms, I mean, the coupling is in a sense of the same size, of the same type, of the same nature. It just, the first says, in the factors in, I mean, the terms in the first equation, they just say that after a random time, a process diffusing on a circle jumps to the lower region. And the boundary condition says the same, except that this is the time to a jump is measured by Levy local time. So you see that these are just boundary conditions, and these terms are just 2 sides of the same coin. They are just expressed in different terms, but they describe the same process in a sense. Okay, and finally, this is a situation where a thin layer approximation is accompanied by a fast diffusion, and it is well known, as I have already said, also that fast diffusion kind of averages out things in a region where diffusion takes place. So if we have a fast diffusion in the lower region, then in the limit we'll have just 1 point instead of the annulus. So if you scale things properly, again you will have a good limit, and this the limit master equation describes the following process. We have a diffusion on a circle, and after an exponential time, the process diffusing on the circle jumps to the center of, described here by a blue dot, and then it spends an exponential time there with parameter beta divided by gamma, and jumps to a randomly chosen point on the circle to start diffusing again, and so on and so forth. So, so in other words, with this thin layer approximation leads to a system of ordinary differential, of a system where you have a PDE coupled with an ODE. Same, and approximation is quite similar. And again, you see now everything that was in transmission conditions is now hidden in, or you may say, it jumped to a master equation. All the coefficients that were in the transmission conditions are now in the master equation, just in perhaps slightly different form. Okay, I think this
time
is almost
slowly running out.
Yeah, I'm almost done. Yeah, take-home message is that Robin type transmission condition and terms describing jumps are to much extent complementary. So they describe almost the same process, just in different terms, in terms of either so-called Levy local time or normal time, regular time, if you will. Okay, and short acknowledgement. Some parts of, first of all, all the work was inspired by Tomasz Lipniacki and Bogdan Kazimierczak's work on kinases, and some parts of the work were done with Markus Kunze, who helped me a lot with dealing with nonlinearities hidden in the process. And I think this is a good time to say thank you all for listening to my talk.
Yeah, thanks a lot, Adam, for your wonderful talk. So I think we are looking forward to questions now, please.
Let me just look. I would like to see you. Okay.
Ryszard Rudnicki, can I ask a question?
Sure.
Okay. You at page probably 4, you mentioned the result of Kurz, but the Lipniacki problem is nonlinear. Yes. Do you use in some way this result, or maybe more ambition question? It is possible to make a Kurz theorem to a nonlinear problem like that?
Well, I have mentioned the name of Markus Kunze, and the bottom line of the result that we have obtained is that if you have, say, Lipschitz continuous nonlinearity in the master equation, then all regular or irregular convergence of semigroups may be handled as follows. You just prove convergence of semigroups, and then convergence of mild solutions to the perturbed equation with Lipschitz continuity, or at least locals continuity, follows. So in other words, this is not I mean, in the regular case of convergence of semigroups to a semigroup that is defined on the entire space, this is really just Gronwall's lemma, and this is pretty obvious. In the non-regular case, this is not obvious, but doable. So the first answer to your question is that non-linearities here are not a big problem. They are locally Lipschitz, and they can be handled quite easily. The biggest problem is boundary conditions. They are non-standard here. There is also, and alluding to your to the second part of your question, there is a theorem by Kurz that treats the nonlinear case. But to be honest, I never really understood how it works. You know, whereas the theory, probably Wolfgang would be able to answer it more better than I do. But the nonlinear theory of linear semigroups has its very subtle points, and so even the question of the way we should understand solutions to this nonlinear problems, I do not completely understand. So this was a more natural way for me to treat linear semigroups, and then just Lipschitz continuous perturbation is something you can take care of later.
Thank you.
We might have time for one more brief question. Anybody?
Hey, maybe just to say hello to my good friend Adam and ask him a short question. I mean, because you mentioned Gronwall lemma, understanding is that all these results are valid on finite time intervals, and therefore there is no information about long-term dynamics, you know, equivalence of long-term dynamics. Have you thought about, I mean, we talked about this some time ago, but have you thought about extension of these results to infinite time?
Well, as you are aware, thinking is not my favorite thing to do. So,
sorry, I didn't say this, but yeah, okay. We can accept this.
No, but this is very interesting but very difficult question. I tend to answer simpler ones.
Okay, okay. So it's time to engage our common synapses. Yes. At certain stage. Okay, thanks.
Okay, so thank you very much. So let us thank Adam Bobrowski again for this wonderful talk.
Thank you.
Okay, so we have 2 minutes break now, and in 2 minutes, the next